Let's work on obtaining equations of motion using Newton-Euler equation. This video clip is a typical posture control study biomechanics experiment. So we applied backward perturbation to the subjects. The subjects are supposed to maintain a balance, and we measure forces and motion and examine what are the mechanisms for the balancing. So to model this, okay, let's start with the human upright posture. Well, if you want to actually model the exact body, there should be many segments working on series, right? However, to make the system simple, we can just start with a single inverted pendulum. The assumption is maybe human motions are approximated as a single pendulum. So if and then since the ground surface has been moved backwards, we can model this as a pendulum inverted pendulum on cart. With Okay, so first, after setting the model, we could define the coordinate. I'm going to set the coordinate at the hinge joint, and then note that this one is moving with the cart is moving with the acceleration of A of O. So I should consider the inertia force applied at the center of mass with the magnitude of MAO. And the draw the free body diagram. So the only contact point of the human with the environment is a ground surface, right? So there's only force uh, a vertical and the horizontal, and there is a joint torque applied. Well, since the foot doesn't move, I can actually move the reference point from the bottom of the foot to the ankle joint. Okay, this is a pictorial expression about how forces are applied, and those are generating acceleration. So the next step is just I can formulate this as a mathematical form. So only x directional force is going to be Fx and MAO. And note that sometimes I just use the vector formulation and the scalar formulation back and forth, so you can actually figure that out, the correct sign convention and expression for the vector. Okay, y forces, there are two, Fy and gravity, so that's Fy minus mg will give you the mi acceleration. And the torque with respect to the point O is torque, the force by the gravity and the inertial force, and just torque tau. So there are three components here: tau, mg, L cross product, and ma, L cross product. And that will generate the I theta, the double dot with the moment of inertia with respect to the with respect to O here. Okay, typo. Okay, now you can actually obtain the moment equation with respect to center of mass g, right? So in that case, you don't have to consider about the torque moment by the gravity and the inertial force. Instead, you should consider anchor joint forces, torque generated by the anchor joint forces, which is L cross product here and cross product y. Of course, with respect to the g, you should have a vector sign minus LC. Okay, so no matter how you set the reference point, either ground anchor joint O or the center of gravity G, you know that those two equations are equivalent, right? So that just obtain the one that you prefer to work with. When you obtain the moment equation in terms of fx and fy, you want to plug that in so that you can reduce the unknown variable. So by plugging Newton's law, second law, F equals ma, you can formulate everything in terms of known AO, and suppose that the surface perturbation profile is given, and you have a AX here and AY there. And for AX and AY, since their center of mass is expressed by sine theta and cosine theta, you can just take the second derivative um, since, so your center of mass is L sine theta cosine theta. You can figure that out what's going to be the L cross product term here. So L cross product term will be expressed by LC cosine theta here, and L cross product term as LC sine theta here. I might just confuse the sign convention here, so maybe plus put the minus sign there, but I'm pretty sure you can work on it. Okay, the next step is how we can eliminate AX and AY. Since we know the position in terms of the theta, we can take a second derivative to obtain the acceleration, which is now expressed by theta double dot plus LC theta dot square, right? And by multiplying a LC cosine theta term and LC sine theta term, you can actually simplify all those multiplication form as LC square theta double dot. So if we rewrite everything, the torque components will be the torque at the ankle and the torque by the, sorry, it's O here, by the cart backward propagation, acceleration, and the torque by the gravity. And those are the three components applied the torque to the system. And your acceleration is going to be related about the moment of inertia with respect to the center of gravity, and its offset with respect to the point O. Okay, so suppose that you assume that human posture balance are performed by a single pendulum way. So, and then you can make a model and obtain the solution. And it looks like your data looks quite different from your model. What's going to be your next step? You should modify your model, right? So after I examined the human posture control, I figured that out there is a huge amount of hip joint motion, which is not negligible. So you should use the second segment um, take into account for your model. So suppose now I'm extending my previously single inverted pendulum as a double inverted pendulum, still on a cart. How can I obtain the equations of motion? Well, pretty much a similar way. First thing is you should actually define the coordinate at the angle joint here, right? And note that this acceleration, so I could apply the inertial force at the center of mass of the lower body. And if I took out the lower body, detach the lower body, there is only used to be only one contact with the ground, but in this case, you have two contacts, one with the ground point and the other is from the upper body. So there are two contact points. So there are forces applied from the bottom and the top, right? So after drawing all the forces on the free body diagram, the next step is you can just convert this pictorial expression for force into a mathematical expression. So there are three forces in the x direction: Fx, Fx1, Fx2, and inertial force. And y direction, same. Fx, Fy1, Fy2, and the gravity. And for the torque, now here I'm calculating with respect to the g so that I don't have to consider about the inertial force due to the moment due to the inertial force and the gravity. So there are total six components because I have Fx, Fy, and tau 1 at the ankle, Fx2, Fy2, and tau 2 at the hip joint. So I have total six components right here and like this, okay? So that'll generate the I theta double dot with the moment of inertia defined at the center of mass. Okay, now let's work on the equations of motion derivation for the upper part. So upper segment has only one contact with the lower body. So there is only force applied from the lower body, which is Fx2, Fi2, and tau 2. Of course, these are action-reaction pair and the gravity, and that's it. So is that it? Well, yeah, I missed one, which is the inertial force, because when I set the coordinate at P, okay, P is moving. The lower body at end point of the lower body it moves with the acceleration. Therefore, you should also consider the inertial force at this point, joint P, right, as a form of MAP, directing the opposite. So, by completing a free body diagram, pictorial expression for the forces and acceleration, then you can just convert this pictorial expression into mathematical form. So your mathematical form shows that, oops, you have two x directional force components, Fx2 and the inertial force, and y components as 2, Fy and the gravity. And since you are obtaining moment equation with respect to center of mass, you only have three components, which is tau 2, moment by Fx2, moment by Fy2. Okay, so this is how you can obtain equations of motion for the multi-segment rigid body. So if you increase the number of segments, you can just repeat the similar steps. And note that since you are putting the reference coordinate at each joint, when you actually set the reference coordinate at each joint, you have to consider the inertial force. Okay, so suppose that this technique could be used to when you want to model those human motion with the acceleration. And suppose that I want to analyze the upper arm, okay, right arm, the throwing arm biomechanics. Then just keep focusing on the throwing arm here. Oops, throwing throwing arm here, okay, and maybe I could set the reference point at the shoulder. That will be easier to putting it this contact boot because in this case you should actually consider all the body segments. So I'm going to set the reference point at the shoulder. So maybe two segments, arm, forearm, and the lower arm. Motion behavior like it looks like this, and note that this hinge point moves with the acceleration, right? Up and down, two-dimensional or even three-dimensional acceleration profile. So it'll not only having two segments rigid body, I can also put the basement acceleration like a two-segment pendulum on the cart kind of case. And then here acceleration is not only just a horizontal, it's maybe had a two-dimensional profile or three-dimensional profiles. This is how you can apply your modeling knowledge for the human body segment. And I strongly encourage you to work on the motion you are interested in to analyze, interested in analyzing.